Calculus. So 2, 5, going to do 11 through 30 here. And the directions here say find values of x, if any, at which f is not continuous. And you kind of know about this already, right, from pre-calc, because we're really just talking about domain and domain restrictions and stuff like that. It's just that now we're combining that with the language of limits and seeing how we can talk about discontinuity and continuity using that new language of limits. So for the first one, number 11, I'm not going to copy down the functions for these first few, just in the interest of time. We've just got a polynomial here for 5x to the fourth minus 3x plus 7. And there's no problems there. There's no denominator that could be equal to 0. There's no root sign that you can't have a negative under or anything like that. So there are there's no discontinuities. They're asking us to say where it's not continuous. So there are no places. There's none. Oh, look at me. I'm skipping to do odds, and I'm supposed to do all of them. So number 12, oh, I got a root sign, but it's a cube root sign, and you can take cube roots of negative numbers, no problem. Like the cube root of -1 is just -1. Cube root of -8 is -2, and so on. So there's no problems with that, and there's no denominator. So there's no discontinuities, none. Number 13, oh, there's a denominator. So any place where the denominator is equal to 0 is going to be a discontinuity. But if you look at that denominator, you've got an x squared. That smallest x squared can get is 0, can't be negative, and then I'm adding 4, so that's actually never going to be equal to 0. If you think about, I don't know how visual you are about these things. I am. So x squared plus 4 looks like this, right? That never crosses the x-axis. It's never equal to 0. So that denominator is not going to cause any continuity issues. All right, number 14. All right, now we're talking. So in the denominator here, I've got x squared. I could factor like this. So x can, the places where it's not continuous are at x equals 2 and -2. Now, if you're thinking to yourself, wait a minute, can't I just cancel out the, can I cancel these out and then I don't have to worry about the -2? I could cross that one off. And the answer is, well, this does factor and those do cancel, except you can't cancel out a 0 over 0. So those cancel all the time for all values of x. That canceling is totally legit, except when x equals -2. Because if x is -2, then these things are equal to zeros, and you can't just cross out a 0 over 0. That is not allowed. So even though those do cancel out, they don't cancel out when x is equal to -2, and that means we still are going to get that discontinuity there. Right? So more about that soon. I think, wait, where did you already do that? Hold on, I'm just trying to, no, you've already done that. So you understand the way limits cancel and how that would work. So this is still a discontinuity. All right, blah, blah, blah. In number 15, I've got 2x, got x on the top, 2x squared plus x on the bottom, so that denominator can't be 0. So let's see, I'm going to do a little factoring here. I'm going to factor out an x, which leaves 2x plus 1. What makes this equal? So it looks like x equals -1/2 is going to be my problem spot. And also x equals 0 are what I get from those two factors. Those are the things that make the denominator equal to 0. Number 16, let's see, on the bottom I've got this 4x squared plus All right. I'm going to sniff around for a second, but that does not factor. And so what do we do now? Well, I guess you could quadratic formula that. I don't know how familiar you are or how intuitive you are maybe about little quadratics like this. This is kind of close to a perfect square. 4x squared plus 4x plus 1, that's equal to 2x plus 1 squared. You can FOIL that out if you don't believe me. But that's what you would get there. Now this thing here is 4x squared plus 4x plus 1 plus 4, because we had to get that up to 5. So if you take something that's a perfect square, kind of like we had in number 13, where you had that x squared plus 4, this cannot ever be negative because we're squaring something. The smallest it can get is 0. And then I'm adding 4. So this actually is never going to get negative. So there are no discontinuities there. That's a little tricky. The other thing you could do, if you think about your quadratic formula, the thing that makes the difference here, if you're really going to get zeros or not, is this, right? The b squared minus 4ac. If that's positive, then you're talking about having real zeros. But if this is negative, then you're talking about something that exists entirely above or perhaps below and never crosses the x-axis. So this is that discriminant because it's the thing that discriminates or can tell the difference between the things that cross or do not cross the x-axis. So we could do a quick check with that. So what's the discriminant here? It would be b squared minus 4 times 4 times 5, and that is some kind of negative number. So that means I have no real zeros, no crossings, which means that this is never equal to 0, which means I have no discontinuities. Number 17, okay, I got two separate things here, so none of the denominators can be, or neither of them, can be equal to 0. So that means x equals 0, that's going to be discontinuity, and plus or minus 1 also going to cause problems. Number 18, let's see, excuse me for 1 second, just make sure I'm in the right place. Okay, 18 is similar to 17. X can't be 0, and x can't be negative 4. Got to look at both denominators. Okay, number 19. I've got on the bottom of this, I've got the absolute value of x plus 3. So the thing that this would have to be equal to negative 3 to make the bottom equal to 0. So what values of x, for what values of x is the absolute value of x equal to negative 3? None. That can't happen because it's in absolute value signs. So that's going to be fine. All good. Can't be negative. This can't be negative, which means that can't be 0. All right. 20. Big thing in absolute value signs. So the only issue here, just like in these other problems, you can take the absolute value of 0. So the fact that there's big absolute value signs doesn't really make any difference at all here. The only issue or potential issue is this right here being equal to 0. So I'm going to factor that, x times x cubed plus 1, and this, so that's 0, and this, when you cube negative 1, you get negative 1. That's going to make that 0. So there's my discontinuities at 0 and negative 1. Number 21. Ah, interesting. Okay, so now this is super important for us to understand that in a piecewise defined function, I get 2x plus 3, that's one piece, and I get 7 plus 16 over x. I don't know, I guess probably you just don't spend as much time as I would like with piecewise functions in pre-calc or algebra 2 or whatever. So I think what I find is often students come to calculus not really being super familiar or super comfortable with this piecewise function business. What do we have to check here? Well, first of all, what is a piecewise function? Piecewise function is saying, look, when x is less than or equal to negative to 4, then you're going to use this to decide what the function is equal to. But when x is greater than 4, you're going to use this. If that seems like a stupid game to play, then I just have to tell you you're completely wrong. There's lots of things in the world that can be modeled with piecewise functions, and there's lots of things where you just need to have piecewise functions to model things. It's not like all functions. It's not like something behaves the same all the time. Sometimes things get to some threshold and then things change. So you think like, I don't know, chemistry with phases of things, and there's many examples in the natural world and also the human created world where piecewise functions are the way to go. So anyway, what do when we're thinking about this, about continuity with piecewise functions, there's two things that we have to check. We have to check the individual pieces for problems and then see if the problems are in the little subdomains. But we also have to check the place where it transitions from being one rule to the other. Because those two things, you could have, since this is the equal part, whatever this is doing, it's cooking along here, and when it gets to 4, it's going to dead end there, right? It gets a closed circle here because this is where the equals is. And then this thing, whatever that looks like, is going to pick up somewhere with an open circle because it doesn't have an equal sign. And there's two things that could happen. It can either match up. They can either match up like this and be continuous, or they can miss each other. So you have to check and plug that 4 into both of these to see if you get the same thing. I've had many students who resist plugging the 4 into the one that doesn't have the equal sign. They're like, why am I plugging the 4 into this one? Because there's no equal sign there. Well, what you're doing, you're checking where the open circle is. Right? There's no equal sign, but there's still, like, that's where it dead ends, right? Because you can, x greater than 4, that includes 4.00000000000000000000001 and numbers like that. So, I mean, that's super close to 4. So if you want to know where the dead end is, where the circle is, then you got to plug in 4 to this. And it doesn't matter that there's no equal sign there. We're just checking to see where that open circle is. So, that's what we need to do. So first, do we have any problems with this piece? Are there any discontinuities here? That's just a straight line, no problems. Okay? Here, are there any problems? Yes. You cannot plug 0 in here, right? Because that's going to cause a divide by 0 error. But the next thing we do is we look at this. 0 is not part of this subdomain. So although you can't plug 0 into this, that's okay here because you're not going to be plugging 0 in. If you come along with an x equals 0 to this piecewise function, you should be directed to this piece here, right? Because this is that x is less than or equal to 4. Hey, 0 is less than or equal to 4, so you would plug in here, not here. So initially you might look at that and say, oh, x equals 0 is a problem, but it's not a problem because that's not the piece you would be using when you have x equals 0. Okay, so the last thing we need to check is, do the pieces match up to each other? So I plug 4 into this, and I get 2 times 4 plus 3 is 11. And then I plug 4 into this, 16 divided by 4 is 4 plus 7 is 11. So the two pieces match up. So we are all good here, which means that the answer is none. There are no discontinuities. So there's a little bit of work to determine that, and I know I really beat that one to death. But there you go. Now it's dead, so we can move on. So that's how you have to think with piecewise functions. So we'll go through this one a little faster. So this time I've got pieces 3 over x minus 1 when x is not equal to 1, and 3 when x is equal to 1. Okay, well, what's going on here? So this is just this function is a horizontal line. F of x equals 3. Oh, just kidding. It's not a horizontal line. This function is equal to this thing, right? What does this look like? Let's see. Can't plug in 1, not because it says so here, but because you can't plug in 1 because you would get 3 over 0. So this is a function that just looks like, oops, I think I put that piece. It should be here and here. It looks something like that. It's just like your 1 over x function. It's stretched in the vertical direction and shifted over 1 to the right. And then when x is equal to 1, you're going to use this piece instead of just saying, oh, can't do that. There's a little plug here, so you can plug in 1 with this piecewise function, and you get 3. So that puts a point right there. Now, is that continuous at x equals 1? No. So at x equals 1, it is not continuous. Try as you might, you can't just like insert a point and fix a vertical asymptote. We have 3 different kinds of discontinuities. We have holes, jumps, and vertical asymptotes. The only kind that can be like patched up, where you can take a function and kind of fix it without just really completely changing it, is a hole. If you have a function that's going along and it's got a hole in it, well, you could insert point at right location and then make it continuous without changing the character of the function. All right, so more about that soon. Number 23, A. I've got, let's see, f of x. What are my directions here? So, sorry, let me back up for a sec. Find a value of the constant k, if possible, that will make the function continuous everywhere. Okay. Sorry, no pun intended there. 7x minus 2. You know what? I don't know why I'm trying to crowd that in here. Need a new piece of paper. So 23, a little more room here. A. Got f of x is equal to 7x minus 2 when x is less than or equal to 1, and k x squared when x is greater than 1. All right, that's all fine, great. You know, this thing right here, that doesn't have any problems, and this doesn't have any problems. That's not really what this is about. What this is about is making the two pieces of the piecewise function match up to each other. So this is some kind of line here. Because it has the equal sign on this piece, that's where the closed circle is going to be. This is some kind of parabola, so that's going to have the open circle. And depending on this value of k, I can tweak this piece to move this around, right, and try to get those two to match up. So how do you do that? Well, you just set them equal to each other. What you need at x equals 1, when I plug 1 into this, right, and I plug 1 into this, if those two things don't match up, in other words, if they're not equal to each other, sorry, I did that wrong. Let me write it. I'm plugging 1 in for x, so that's k times 1 squared. That's what I meant to write. These two things have to be equal to each other if they're going to link up. So let's see. That's 5 and that's k, so k has to be 5. If k is 5, the two pieces link up. And the little dot ends up right in the little hole, and everybody's happy, and it's continuous. I don't know if continuity makes you happy. Maybe. Maybe it doesn't. All right, so this is B. Same game. I just have to plug 2 in for x and make those equal to each other. Again, I've had many students who object here. They're like, there's no equal sign there. How am I can't plug 2 into that? Yes, you can. You're locating the hole. Although x equaling 2 never happens here, you can still plug 2 in here to see where it ends up, what it's approaching. It's a limit. All right, so let's see. I plug 2 in here, and I get 4k. And then I plug 2 in here, and I get 4 plus k. And then I do some algebra, and it looks like k is going to have to be equal to 4/3. That's all, folks. So here, let's see what we got. I got f of x is equal to 9 minus x squared when x is greater than or equal to -3, and k over x squared when x is less than -3. Now this has issues here with the 0 when x is less than -3. Oh, but we're okay because if you're plugging 0 into this, you're not going to be using this anyway. You're going to be using, because 0 is greater than or equal to -3, you're going to be using this piece. So I don't have to think about that problem. I just need to see if I can find a k that makes these equal when I plug in -3. So plugging -3 in here, I get 9 minus 9, mostly 0. That's equal to. And then I plug -3 in here, I get k over 9. So 0 is equal to k over 9. So that's looking pretty much like I'm going to have k be equal to 0. So let's see, if k is equal to 0, then hold on 1 second. Yeah, then we're good. So, sorry, I was just checking in the solution manual. I was looking in the wrong place and seeing a different answer than that, but I was looking at the wrong problem. So k equals 0 is correct. All right, for B, got, it's the same function. 9 minus x squared. Oops, don't know why I wrote that there. And k over x squared. But this time, the transition happens at 0. So how does that change things? Well, that's now I'm plugging 0 into these. Oh, and now here, we got a problem here because 0, we can't fix this here at 0 because you're going to have an asymptote there. So plugging 0 into this, even though it's not equal to that, I would have to make this link up. But this is going to approach infinity, or positive infinity, when we come up to 0 here. So this, we cannot fix it. No value of k is going to work there. Because if we plug that in, if we plug 0 in, I get k over 0, trying to make that equal to plug x equals 0. There's no value of k that when you divide it by 0 is going to be equal to 9. This is undefined here, so can't do it. Can't be fixed. Sorry. Number 25. Let's see, find the values of k and m if possible that will make the function f continuous everywhere. Okay, this is the same game, it's just a little bit more complicated. So I've got x squared plus 5 when x is greater than 2, and then m times x plus 1 plus k when x is in between -1 and 2, and then 2x cubed plus x plus 7 when x is less than or equal to -1. Okay, so there's two transitions here. Here, when x crosses over 2, when it transitions from being greater than 2 to being less than 2, these are the two pieces that we're talking about. So that means when I plug x equals 2 into this, right? When you plug x equals 2 in here, you get 9. And when I plug x equals 2 into this, let's see, 2 plus 1 is 3, it'd be 3m plus k. Those two things would have to be equal to each other. If we want them to link up, then at that transition, right, this is when it's greater than 2, this is when it's less than 2, so those two would have to be equal to each other when x is 2. So that the open circle and the closed dot link up. Now here, it's transitioning from -1 being above -1 to being below -1. So when I plug x equals -1 into these two, they would have to be equal. So -1 in here, that would be 0, so that's just k. That would have to be equal to, when I plug -1 in here, I get -2 minus 1 plus 7. So it looks like k would have to be 4, and then if I plug that back in here, it looks like m would have to be 5/3. Right. And just double check, make sure I didn't mess up any algebra there. Yep, that's good. 26. On which of the following intervals is f of x equal to 1 over the square root of x minus 2 continuous? And we've got some choices here. So is it continuous on the interval from 2, the square bracket means it includes 2, to positive infinity? Is it continuous on that interval? Well, no, because if I plug 2 in, this means includes 2. I can't plug 2 in because I'd get a 0 on the bottom. So, nope, sorry. How about from negative infinity to positive infinity? That's being continuous everywhere, and I think if we found a problem, then it definitely isn't continuous everywhere. How about from 2 to infinity? That's open parentheses, so that means that it doesn't include 2. That's like the same as saying x is, this interval here is the same as this interval here. X greater than 2, that's good because it doesn't include 2, so I don't get the 0, and greater than 2 is good because then I'm taking square roots of positive numbers. How about on the closed interval from 1, sorry, closed 1 to open on 2, that's the same as that. So that's no good because I can't plug in numbers like 1.5. Anything less than 2 is going to make this negative, so that's no good. So just C. All right, 27, we're almost there. All right, so function is said to have a removable discontinuity if blah, blah, blah. Basically, all that says is that it's a whole. So can we fix these things? So 27a, sketch the graph of a function with a removable discontinuity at x equals c, for which f of c is undefined. So what that means is a function with a hole. So anything, I mean, you could draw absolutely anything where there's x equals c. There's a hole there. There's no point on that function. That's A. Sketch the graph of a function with a removable discontinuity where f of c is defined. So it's a removable discontinuity. That's got to be a hole. If f of c is defined and it's still discontinuous there, that just means that f of c, like that point, is like in the wrong place. So that's what those graphs might look like. 20, oh, I think I haven't, that's not enough room there. Let's flip over here. So 28. So what value for f of c removes the discontinuity? So if you've got, that might seem like there's not enough information here. What they're getting at here is if you've got a hole, then what would you have to plug the hole with? What would f of c have to be equal to fix it? Well, f of c is not defined, so I can't just say f of c equals f of c, because there is no f of c. The thing that you would have to put there is the thing that it's getting closer and closer to. So f of c, to fix it, you'd have to make f of c equal to whatever you're getting closer and closer to as you approach the hole. If you want to patch the hole, then make f of c equal to the limit as x approaches c of f of x. And that is true for any hole. That's how you would have to patch it. That's what they're getting at there. For 28b, show the following functions have removable discontinuities and sketch their graphs. So removable discontinuity, remember, just means hole. So what does f of x equals x squared minus 1 over x minus 1 look like? Well, x squared minus 1 factors into x plus 1, x minus 1, and these two things cancel out for all values of x except for x equals 1. When x equals 1, you get a 0 over 0. You can't do that. So that's where the hole is. The hole is at x equals 1. And if you cross those out, you can see the thing that it must be approaching when you plug 1 into this, it must be approaching 2. So the hole's at x equals 1, point 1 comma 2. And otherwise, this thing is just the line x plus 1. Well, it looks like this. It's just the line x plus 1, but when you get to x equals 1, there's a hole there. And as soon as you pass x equals 1, then you're just back to this again. The only problem is when x is equal to 1. So the graph would look like that. And then this other one is a piecewise function that is equal to, when x is greater than 1, it's just equal to 1. When x equals 1, then the function is equal to 0. That's the middle piece. And when x is less than 1, then it's just equal to 1 again. So it's just a horizontal line with the point in the wrong place. So back to like 27, that's an example of one where f of c is defined, but it's in the wrong place. So can you fix that? Yeah. Do you just get rid of that point and then put it in the right place? So c, what values should be assigned to f of 1 and g of 1 to remove the discontinuities? So for this one, you would want f of 1 to be equal to 2. Right? And notice f of 1 would have to be equal to the limit as x approaches 1 of your function. Right, that's just like a factor and cancel job there. So here, right, in all cases it has to be equal to whatever the limit is as you approach where the hole is. And then here, what would g of 1 have to be equal to? It would have to be equal to 1. to put that in the right place. All right, number 29 and 30, and then I think we're done. Always trying to keep this under half an hour. I hope you're just skipping through this and using the bits that you need. All right, so problems with absolute value signs, that's a thing. What does this f of x equals this absolute value of x over x, what does that look like? This is a favorite of calculus teachers everywhere. So when x is positive, then these two numbers are just the same because the absolute value signs don't do anything. And if you have same number over same number, then that's just equal to 1. But you can't plug in 0 because you get 0 over 0, so there's an open circle there. And what about when x is negative? Well, when x is negative, this is going to be some negative number, and this is going to be the positive version of the same number. So positive number over negative same is going to give you -1 every time, but you still can't plug in 0. So it looks like these two little horizontal bits. Okay, so this is not continuous at x equals 0. And is it removable? No. It's not. This is not a hole. This is a jump discontinuity. So it's not removable. And there's no E there in removable. Sorry, extra letter there, bonus letter. B. No absolute value signs here, so what do we have here? F of x is equal to x squared plus 3x over x plus 3. So -3, that's a problem here for discontinuity. Now the only way that that's going to be a hole is if the same exact factor shows up on the top. If this cancels out on the top, or if it can cancel out, if it has the same factor, I should say, on the top, then it's a hole. And in this case, we got the same factor top and bottom. So this is not continuous at x equals -3, but it is removable, which just means that it's a hole. If the same factor, if that factor cancels out top and bottom, then it is a hole. Part C, I got another absolute value dealio here. I'm going to move over to here. This is a little tricky. Do they want us to sketch this? Where are the values determined? They don't want us to sketch that, so that's okay. Just got to figure out what's going on here. X minus 2 over absolute value x minus 2. This is tricky to think about. So what are the issues here? There's possible issues here when x is equal to 2 and when x is equal to -2. When x is equal to 2, then we're hanging around in positive territory. So when x is equal to any positive number, the absolute value signs aren't doing anything. So in positive territory, or in other words, when x is greater than or equal to 0, the absolute value of x is just equal to x. So in the bottom, that's just like x minus 2, and there you have same factor top and bottom. So you can't plug in 2 because you get 0 over 0, but you can fix it because it's the same factor on the top and the bottom. So this is removable, or in other words, it's a hole. Now how about when x is equal to -2? In negative territory, in the negatives, or when x is less than 0, then the absolute value of x is equal to -x. So then that would be like the bottom of this is -x minus 2. That is not the same as this. So that is not the same factor, and that means this is not removable. think that's a little tricky. But it's a good one. Number 30, last one. Can I squeeze it in here? Maybe. So 30a, I've got half of x equals, sorry, I'm trying to go fast, making a mess, is equal to x squared minus 4 over x cubed minus 8. So let's see, on the top there, that's x plus 2, x minus 2. I'm factoring these because that's what determines whether it's a whole or not. It's a whole if the same factor shows up on the top and the bottom. And then on the bottom, I don't know if you remember how to factor the difference of two cubes, but I know when I plug 2 into this that I definitely get 0. So that means x minus 2 has to be a factor of it. And if you know that, you can actually just do synthetic division to figure out what the rest of it is. If x minus 2 is a factor, well, if you run 2 through the synthetic division of this, then drop the 1, 2 times 1 is 2, plus 0 is 2, 2 times 2 is 4, plus 0 is 4, 2 times 4, and I bet I get a 0 there. If I didn't get a 0 there, then that's a sign that I messed it up. So there's my coefficients. This is going to be a good trick that we're going to use in some places in Chapter 3 too. I think that's going to come back. So maybe you remembered that the way to factor the difference of two cubes. Maybe you didn't. If you don't remember, or if it's some other funky thing that you have to factor that's higher than just power 2, then you can use this trick because we know what one of the factors has to be. It's a giveaway. I know that the 2 cubed, that's 8, so you can use that trick. All right, so this, at x equals 2, we have a whole, or in other words, a removable discontinuity. And this thing here is always positive, right? X squared plus 2x plus 1 is a perfect square, and then plus 3 more, so that's always above the axis. So there's only one problem spot here at x equals 2, and it is a whole because the same factor shows up there. So that's 30A. Oh, and they want us to, so can you plug, if it's a whole, then you could plug it. So if you want to fix it or plug the whole, then what does f of 2 have to equal? Well, if you go ahead and cancel this out and then plug in the 2 here and here, I get 4 over 4 plus 4 plus 4, so I get 1/3. In other words, if I just evaluate the limit, what am I doing here? I'm really just finding the limit as x. Sorry, folks, you can see some of that stuff. The limit as x approaches 2 of x squared minus 4 or x cubed minus 8. Factor and cancel. Plug it in. You get 1/3. And looks like I need another piece of paper. 30b. Piecewise. Got 2x minus 3 and x squared. So there's no issues with the pieces. I just have to check where it transitions here. So plug in the 2 in here, I get 1. Plug in the 2 in here, I get 4. So this is not continuous at x equals 2. And it can't be fixed. It's not a whole. It's a jump. So it can't be fixed. So we're done with that one. Part C, another piecewise. F of x is equal to 3x squared plus 5 when x is not 1, and 6 when x is 1. So got to see if they match up. So plug 1 in here, I get 8. Plug 1 in here, well, there's nowhere to plug it in. You just get 6 all the time. So it's like this point is in the wrong place here. So to fix that, so at x equals 1, we got a problem, but I could fix it by making f of x, or making f of 1 equal to 8. That's what it should be if you don't want to have that whole problem. All right, that's it. That's kind of a long 45-minute homework video. Hopefully you didn't have to watch the whole thing. There you go.